what are its components and parts. Now, basically, the thing is that here we have MLs or ML practitioners, and we have only one thing in our mind: we want to do ML with JAX. Like I interrupted Orithro in the middle to say that you can even build game engines with JAX. I actually have done that, but we are not here to do those kind of shenanigans. We are here to do ML with JAX. Now, yeah, the go-to solution. Everyone uses flags, right? By the way, can anyone tell me what is the meaning of the word flags?
Flexible.
No, not even that. Sorry, you are very close actually.
Something JAX like.
Obviously, something JAX. तभी तो मैं बोल रहा हूँ. I meant what is the I asked what is the meaning of the word flags and not what flags is.
And it's also in English, right? It's asked around
It's,
that rice.
yeah, you are actually right. So it's a seed, okay, seed of rice. And this is the logo of flags.
Nah.
Now, this is what flags claims they are basically. Okay. So they claim that they are a high performance neural network library for JAX designed for flexible and performance. So flexibility, FL flag. And obviously it's JAX, so flags, so the nomenclature. And it's a library actually that's maintained by Google itself, like JAX. But here's the question: why do we need flags?
Because yes.
Yes, that's actually true. Is it keras for JAX? Like, can we say it's keras for JAX?
Not even close, but yeah. Big no.
But here's the thing: for those of us who have worked with keras, like we know, right? The object-oriented paradigm is intertwined with the design philosophy of keras, right? And we just now learned that JAX doesn't like stateful objects. So, flags asks this very question: can we have keras for JAX? In fact, I use this meme to actually taunt the pie torturers of Twitter. But whatever. Is it PyTorch for JAX, by the way? Because PyTorch, like with all its flaws and all, PyTorch is still pretty good. Don't throw shoes. Okay, so here's the thing. What we need is, we basically need a high-level API on top of JAX, which can help us build our machine learning pipelines, which can help us build our models in a semantically Pythonic manner. We need some utilities which will help us to create our training and validation pipelines. That's all we kind of need, right? This is basically what keras does for TensorFlow, right? Now, we already have TensorFlow and PyTorch, and we do not need a clone of either. TensorFlow and PyTorch, they are both pretty similar in scope, and they live in their own world. And since we have already learned that JAX is pretty functional in nature, we cannot borrow from the paradigm, like we cannot adapt the paradigms of design which TensorFlow and PyTorch uses. So TensorFlow has its own training APIs, keras, which is the best thing in the whole world. PyTorch has its own keras clones or cheap knockoffs, as they call it, lightning. I'm not afraid. You can quote me on that. That was actually quoted by, in fact, François Chollet, the creator of keras himself. This is not something which I tell. So, if we have a high-level API on top of JAX, how would it be more advantageous to us with respect to Keras or PyTorch or PyTorch Lightning, any of the training APIs which are available for these frameworks? So one of the things that we already kind of saw very cool is that the composable functional transfers, right? So they kind of are really cool, and they kind of helps us build a push forward the notion of machine learning push forward the notion of developing machine learning pipelines a lot. For example, like Orithrom had mentioned that he had encountered a workflow, a machine learning workflow, tried to code that in TensorFlow, which it consisted of multiple orders of derivative. And how this looks in TensorFlow? With tf.gradient as step 1, with tf.gradient as step, with tf.gradient as step, right? That's just not scalable. And how would this workflow look in JAX? JAX.grad of, JAX.grad of, JAX.grad of. You can put a for loop and inside JAX.grad of the previous function. You can do that. That's as simple as that in JAX.
Why can't we do Hessians?
Sorry?
Why can't we do Hessians? Hessians is a second derivative form only.
Yes.
For TensorFlow. We had queries.
So we kind of get an idea that these kind of APIs are more maintainable. They are more scalable. We kind of already touched upon the scalable factor of JAX, right? The composable function transforms, and these kind of code bases are more maintainable in the sense that you already have written your code once. You can adapt it to not just new accelerators or new setups, but also you can add more functionality to your existing code base very easily. And as Orithro has already mentioned, speed and JAX are the best friends together. So JAX is supposed to be more performant than the existing libraries, right? And definitely more performant than PyTorch. Let's pull some linen from our flax seeds, that is right. So linen is the neural network API that resides inside this library called flax, which helps us build neural network models in a very flexible and Pythonic manner. Okay. Now, what linen enables us to do is, it enables us to write models as single example code. And what I mean by single example code is basically the way we, subclass tf.keras.model, or if you are a PyTorch user, you subclass for nn.module. So that way of writing code is called single example code. So here's the thing. The best thing about the linen API being single example, supporting single example code means that your neural network code does not look significantly different from your Keras or your PyTorch models which you have already coded. So it's actually very easy to port your Keras and PyTorch module to JAX using the flags.linen API. Introduce batching automatically by virtue of VMAP, right, which Orithro has already touched upon, and I won't waste much time discussing it. Now, here's a couple of interesting things. So, linen provides you a couple of utilities, let's just call it, which enable you to make your neural network code more performant, not just in terms of speed, but also in terms of memory footprint. So remat or rematerialization is a full paradigm. So it's one technique that's used to make your neural network code more performant in terms of memory footprint. And there's another paradigm which is called reversibility. So these are all paradigms which are very which make your neural network not just training but your inference workflows as well very performant, and make your training and inference workflows very performant. And if you want to delve into detail with respect to how remat and what exactly remat and reversibility works, this slide is actually available to will be made available to everyone. You can check the speaker notes of these respective slides. Okay. I won't delve into much detail with respect to remat and reversibility because we are kind of short on time and we will be here all day if we start discussing. So I would say let's get our hand dirty a little bit. This basically leads to a collab notebook. You can, in fact, if you want, you can open up your laptop and follow along. We will see how a typical neural network training and validation workflow works in Flax.
Thank God.
So the first thing we do is we install Flax and 1DB. So I'll just make one thing very clear. 1DB is not a necessary component in designing your machine learning workflows with Flax. I just personally prefer to use weights and biases for tracking the loss landscape of my experiments because one, I work for them. Two, it's the best tool. Okay. I do not like matplotlib lots of loss landscape, but that's a personal preference. And we install Flax obviously. It's as simple as just installing it. Okay. So let's do one thing. Let's first connect it to a GPU runtime. Okay, so let's install. Sorry, and these are some basic tools basically which we are gonna install and which we are gonna use. I won't delve much details into the imports or the 1DB init or the config management. I'll jump right into the dataset or the input pipeline. So this notebook basically shows a very simple image classification workflow. We will be using the CPAR10 dataset for classifying the images into multiple classes. Okay. Now, question is that how do we load our data for a JAX or Flax-based machine learning workflow? How do we create that? The answer is again, there's no definite answer to be honest. Right? Some people prefer to use PyTorch data loader to create an input pipeline for their JAX and Flax workflow. Some people prefer to use the TensorFlow TensorFlow datasets, TF.data API. I personally prefer the TensorFlow dataset API because it's faster than PyTorch API, and also when we wish to train on TPU pods, let's say you should actually have your dataset stored as TF records, something called TF records, which basically helps your accelerator to keep it from starving for the data. Okay, so because your input pipeline should not become a bottleneck to your training workflow, right? So the dataset is actually pretty simple. We just use TFDS, which is TensorFlow datasets, which is similar to Torch datasets or whichever dataset catalog you wish to use to load the dataset into a training dataset and a test dataset. We simply normalize elements and map it. The usual TensorFlow dataset building shenanigans. We do nothing else. It's very simple.
May I add something on top of this? So one of the points that should be noted is that there is no dedicated data loaders in the world of JAX or Flax.
Yes.
They dedicate that responsibility to frameworks like TFUG data or Python. They do not have any data loaders. I'm not even kidding. And the recommended way to load data, again, this is a very unbiased thing. I also work with Python a lot. The recommended way to load data in the JAX world is TFUG. Any popular JAX repository you might have seen already, like the vision_transformer repository, which is like the holy grail of JAX code. If you love reading storybooks. I recommend you check that repository out. But yeah, if you go to any popular JAX repositories, you will see they're using TF.data to compose their data input file.
Except a few like JAX Nerf or something like that, like they in fact build their own data loaders from scratch, which
They
is
have to.
Doesn't make any
yes.
sense at all.
No, actually no, they don't have to, but they choose to. That's the difference. You guys have actually proven that you don't need to in your own blog posts.
Yeah.
So yeah, so it's the very simple data loading pipeline. We created a train data set, the brand data set. You know, like Shaida has already shown you a similar pipeline. Won't waste much time on this. Does it run? Takes a little bit time to load, but we will jump right into the one. Like now, if you see, we have built a very simple convolutional neural network, and does this code feel familiar? It feels familiar to PyTorch. Doesn't it feel familiar to TF.keras.model? Anyone here uses subclassed models in TensorFlow or Keras? Arey, two हाथ ना. Okay. Thing is, you can actually create models in a similarly in TensorFlow and Keras also. Okay. So this is what we call single example code. Okay. Now, here's the thing. Okay, one more question. Can anyone identify what neural network architecture this is? Sayagdan, are you sure? You're out of bounds. Anyone else? Yes, what?
6 layers CNN.
No, what is the name of this architecture? What did you say? AlexNet. Yes. This neural network architecture is a very simple AlexNet.
That just won the taste of time over.
Okay. So, yeah, our data loader is ready. So, as you can see, like building neural networks with flags is actually simple, and you can see like we are inheriting from something called nn.module. So, this nn, if you go to the imports and see, this nn is actually linen. So, from flags import linen as nn. It's just like you import the nn.module from torch. It's very simple. Right? And so runs.
Do we need the setup function?
No, that's actually a very good question. No, I prefer it. It basically teaches those very particular TF.keras structures I have. Features I have. Yes. Shaida is actually a very good point that we do not need the setup function. Are you guys used to defining Keras models in a functional manner, like using the module where, like calling the module where you are defining it? Do you use it that way, or do you guys?
Torch functionally.
Sorry.
We use the torch functionally. Like I personally use that.
Okay.
The torch function.
Okay, we are not best friends. So okay. So it's like yeah, basically you can actually define your modules, flags modules, in a very similar manner to Keras functional paradigms. So in that case, basically what happens, you do not need this setup function. All you need to do is mention that this by default that this call function, the forward propagation, is a compare function. Okay. Now here's the thing. In an ideal world, in PyTorch or Keras, how we define model is something like this, right? Model equal to the module class. We just instantiate the module class, and then we have everything. But as Auditory and Rhetoric has iterated multiple times that, in JAX is functional. Everything is functional. There's no concept of stateful programming in JAX. So in PyTorch and Keras, we are kind of used to having the weights as states of the model itself, right? But here, that's not the case. So this model that we actually created just now, it's nothing but a data class which abstracts a few functions with respect to forward propagation. Okay, nothing else. It doesn't have the states of the model included. But that doesn't mean we don't need the states, right? We need the states still. We need the trainable parameters of the model, right? And as you can see in this particular piece of code, we are actually initializing it separately. Instantiating the flags module does not automatically create your weights. You have to create it by default. So what do? We define a dummy tensor of size 1, 32, 3, whatever your batch says. It's your batch dimension, okay? And we use that tensor to define the parameters. And these parameters will form part of our state, which we will be handling separately, not as a part or as a member of the module. Okay. So if you just
There's a question.
Sure.
So when we write model in TensorFlow using subclass paradigm, and if you want to inspect the model, we usually have to use something called dot build.
Yes.
Right?
Yes.
But if we just like do compile it and train it, it will build it automatically and train a model.
Yes.
Do we really need to do it in here?
Yes.
Okay.
We do. Otherwise, your weights will not get created.
Okay.
Because if you are in TensorFlow or Keras or in PyTorch, if you are instantiating your models, your weights get automatically initialized.
So that is done by the Keras.
Yes, that's done by Keras, but that step you will have to do explicitly here, right? Because that's the paradigm, that's the functional
Yeah.
paradigm, right?
I have 2 more questions.
Sure.
First is there any advantage of using setup? Second is, what if I wanted to use the same model on a resolution of 64x60?
I'll answer the first question first. So what is the advantage of using setup? The advantage is purely semantic, as it's mentioned in the flags documentation.
Yeah.
So it's just to make your code more Pythonic.
Yeah.
Nothing else. And what if you want to use it on a resolution?
Different resolution.
Different resolution. So the very simple
Also,
answer.
let me put more context. In the Keras code, we usually define the placeholder like 9,3. How is that treated in this in flags?
Okay. So the very simple answer is you cannot do it like that. So you cannot use the same parameters for inferencing, let's say, on a high resolution. So let's I'll just give you an example of what Shaikara is meaning. Let's say you are training a model for image restoration. Now you want to light up that image. Okay, that image may have been taken in very low exposure, and you want to train a model to so that it automatically fixes the exposure. Now the thing is that you train this particular model on crop sizes or resized formats of 256 by 256, let's say. But you want to perform inference on variable length images, right? That's the thing. Unfortunately, you can't do that. So you will either have to resize it, or you will have to take crops out of it and stitch it together. But since we are working with image classification, it's not a big deal here, because the resolution of the image does not change the resolution of the outputs or anything like that. So that's the kind of answers to the question. So yeah, and as you can see, like the parameters are actually a tree. First and foremost, by tree I mean a very simple nested dictionary of fields. So as you can see, like every the parameter, the frozen dictionary actually has one three like weights and biases corresponding to each and every layer, and yeah, like and the tens and the everything. Now, as we have kind of seen, like JAX uses this in the backend. JAX uses this particular kind of expression format called JAX here. You can actually inspect the JAX layer. You can actually inspect the JAX sphere of your model, and voila, you can actually do that. And actually, if I remember correctly, Christian Garcia, who is one of the maintainers of flags, he has actually built a function called ln.tabular. It is not yet stable. It's not yet stable. But what this function does, it takes in a combination of it makes use of both the JAX sphere and the Actually, an init.tabulate doesn't make use of JAX here. It makes use of your parameters, the pi tree, the parameter dictionary, to build your table so that you can inspect your model in a tabular format, like you do in Keras, tf-keras.models dot sum. And here's an interesting thing. There's another library on top of JAX called Haiku, which is built and maintained by TFUG. Haiku has this particular function where they basically parse the JAX pair of your model to build you complete pi trees and graphs, which you can, like, if you have ever used TensorFlow actually shows you a complete computation graph of your TensorFlow workflow or your TensorFlow model. So Haiku actually has a similar kind of functionality where you can basically export your JAX pair as a graph. So yeah, I won't delve into detail like how this JAX pair is kind of structured. That kind of defeats the whole purpose of this abstraction. I just wanted to show you that yes, you can actually take your flax model and inspect the JAX pairs out of it if you need it. But hopefully this init.tabulate will be stable soon and we won't need to look at JAX pairs ever again.
I have to build a graph of this.
Yes. So now yes, before we jump into this particular function, I want to kind of ask you this. How do we write a training loop in Keras? Can anyone enlighten me?
Do we need to write it?
Yes, and
What can
there is a training loop, right? Under the hood, there is a training loop, right?
Yeah, of course.
Of course, there's a training loop. So I just kind of wanted to strike.
Override your train start.
Exactly. So ef.keras.model is a class which you are subclassing, which your model is a instance of, right? Now here's the thing. Let's say if your training logic requires some shenanigans which your default training logic cannot handle, which Keras's default training logic cannot handle. What do you do then? You override the train step of that particular function and you override the test step of that function for your custom validations step, right? And what happens in PyTorch, my friend?
Yeah, we write the whole forward.
You have to write the whole. Can you give a brief description of what goes inside a PyTorch training loop?
We send the data sets and the path in the data loader and we give the optimizers and the modules.
What exactly it looks like in the back propagation and forward propagation? How does it exactly? Can you give a brief rundown?
Can I explain it?
Chill. It's not an exam, man. Okay, so here's what happens is that you have a loop which loops through how many training steps or epochs, as we call it, you want to train the model for. We loop over the data loader, which is basically an iterator which dumps out our data batches, be it a TF data set or a torch data loader, whatever it is. What I'm saying is basically it's a basic anatomy of a training loop in email. Inside, what you do is you perform forward propagation, you pass the model the data batches, you perform forward propagation, you get the output of the model, you calculate your loss, you update your optimizer accordingly, you update your model weights using your optimizer accordingly, then you basically perform validation against it, and that's basically what a training loop is. Now this whole thing I just discussed, like this taking the data batch, feeding it into the model, getting the model output, calculating the loss, and performing backward propagation. This whole operation is called a train step. This is what goes inside your keras.tf.keras.model.train step. Or if you want to abstract it in terms of PyTorch slightly, there is again a similar function called train step. You have to override there. If you are writing vanilla PyTorch, it's just called train step, right? Now we will come to the fact how we write a train step for JAX and flags, for flags specifically. Okay, but before that, we kind of have to create a train step, because train step is just doesn't consist of our model parameters, there's another component to it. Can someone say what is that? What goes into tf.keras.model.compile?
Loss,
Loss and
matrix,
and
cheat compile flag,
and
and what?
and the optimizer.
Oh,
Okay, so yeah, that's so yeah, so what you can do is basically like we first initialize the variables. Okay, this is a function which basically creates a train state for us. Okay, we initialize the models again. Like previously we initialized just for the sake of demonstration. Here we initialize it seriously. Okay. Then basically what we do is we define an optimizer. Now here for a moment we will go back to the PPT. How do we go back? How do we go back?
close code. Slide show
So in terms of text, which Pavitra had mentioned, so what optex is basically on a very high level, it's basically a library which has your functional optimizers built in. Now, try to understand the fact that in Keras or in PyTorch, your optimizers are actually stateful classes. You are creating your optimizer equal to torch.optim dot whatever the fuck. In Keras, you are creating tf.keras.optimizers.adam or anything like that. So these optimizers are all classes. But as we discussed in JAX, we cannot have what? State. We cannot have state. That means we cannot have stateful optimizers. So all these optimizers have to be defined in a functional way. And what is an optimizer essentially? Can someone say?
something that optimizes.
Of course.
It is a function.
It's a function which
Optimizes. It's another function.
So an optimizer is basically, can we say
Derivative.
yes please?
It uses derivative to basically reduce the function to
Reduce the function or reduce the weights?
This is the weights and the landing path.
To convert to reduce.
Yes. It basically optimizes the weights, right? So what happens is that
Sure.
do we have to stop it?
Don't stop. Just
Okay,
leave
I'll
it
stop.
as well.
Cool. So an optimizer is essentially a function which takes in our new weights, which will take in our old weights and give us our optimized weights. That's all. So these functional optimizers are actually defined inside a library called optex, which is again maintained by DeepMind. And essentially, optex is basically a gradient processing and optimization library for JAX because, as we discussed earlier, JAX is not a library for machine learning. It's a library for scientific computation. And gradient processing is not like machine learning is not the only application of gradient processing. There are lots more. So a lot of these utilities live inside optex, and it's similar to how do I call it? It basically gives you the building blocks for combining your optimizers or define different optimization schedules, learning rate schedules, all these kind of schedules. It basically gives you an easy way to basically combine these different building blocks into one optimizer, which in JAX lingo, which we call TX. Okay. Why? Don't ask me. I did not create JAX, so I don't. So yeah, like you can see all this thing. And let's go back to this. Well, yeah. So we create an optimizer. We combine the variables and the optimizers, and the apply function is basically the model's forward propagation. Okay. We combine all of this into a train state. This train state is a utility provided to us by flags, and it's essentially a data class, so it's not a stateful, you can say state or something like that. Yes, but it's essentially a Python data class which basically keeps track of all these things together. You can use a dictionary if you want. Nobody gives a shit. Just a way. Because Flex gives it, that's why I use it. You can just create a dictionary called of apply function equal to model.apply is equal to optimizer. That's and now we create a very simple cross entropy loss. As you can see, we take the logics and the labels. We one-hot input the labels, and we Optax also provides us with several loss functions. So we apply the softmax cross entropy terms of the logics and labels, and the one-hot input interface, right? And we compute the accuracy metric. I'm not going into details as to how to calculate accuracy. And we have a utility for saving our checkpoints. Okay, so here's the thing, like while training our model, we will be saving our checkpoints. We ideally want to save our checkpoints. So this is basically a utility which lets you to serialize your model into a format called message pack. I hate this particular format, and I wholeheartedly recommend you that you use Hugging Face safe tensors for storing your JAX weights instead of message pack. Message pack is what is recommended by the creators of Flags, but I absolutely hate it. Yes, so that's the case.
Why log it as a dataset artifact?
Sorry?
Why log the checkpoint?
Because I was a moron and I made a mistake. Yeah, ideally that type should be a model artifact, but as I said, I made a mistake. This is what Shai pointed out. This is a mistake. Should be a model. And another function to load artifacts and to accumulate the matrix. By accumulate matrix, all we mean is just do a mean over it along the batch axis. Okay, so that we can convert it into a scalar for the sake of visualization. And now we go into our train state. So forget the jets.chip at jets.chip, forget that. It's a train state. Okay. What is it a function of? It's a function of our train state and our batch, data batch which we will indicate. So right now, as we said, it encompasses a few steps. What are those? First, we use the apply function, and apply function is used for what? Anyone remember? Forward propagation. So first what we do, we get the logics of the model outputs, right? Forward propagation, simple forward propagation. Then what we are doing? We are creating the loss, calculating the loss, okay? By using the previous utility function for cross entropy loss. And now we have kind of this particular function, which is a function of our parameters, of our model's trainable parameters, and it is giving us the losses. Now what we need is basically to calculate the gradients. And how do we do that? What did Orithro say? Anyone? How do we calculate gradients?
Grad.
Good.
I just one question. The batch is NDR, but how are you taking image from a label from a batch?
I'm sorry.
The batch is an NDR, so how are you taking image and label
It's
from a
JMP.NDS.
JMP.
It's a JAX. NumPy.
You can take image and label.
Yes. It's a pie tree. You can say it's a pie tree. So you first create the gradient function. What JAX.grad does it? It gives you another function which basically gives you the gradients. So what we create is first the gradient function using a function which you might not have seen earlier, because Orithro and Ritik showed us JAX.grad. JAX.grad is basically, it's the same thing as JAX.grad, JAX.value and grad, just gives you also the value of the original function. Because we will want to log our losses, we will want to inspect our losses, right? It also gives us the original function and as well as the gradients. So this gradient function, this transform gradient function is being used to not only get the gradients, but also you can get the logics and the grades. The model output also you can do that, right? Then what we do is we dot apply gradients. Remember that utility flags.trainState, and we set our optimizer there. That optimizer we are basically using here. We are applying a RADS to the optimizer. Simple. What is the corresponding PyTorch step? Can someone tell me? Okay. And what is the corresponding Keras step? Keras step? No. How do we apply the gradients to the
Oh,
optimizer?
gradient dot optimizer dot apply gradient. Apply
Exactly.
gradients, exactly.
So it's the same nomenclature, but in a functional manner. So what this whole trainState function is doing, it's doing forward pass. It's calculating the gradients. It's applying the gradients to the optimizer for back propagation, and it's calculating the matrix on top of the training batch. And we have done one small little thing. What at JAX.g. What does this mean is that you can interpret this as trainState equal to JAX.g of trainState. A decorator is essentially a function which takes a function and converts it into another function. So that's how basically we, for the sake of our convenience, we just use the decorator. And what do we do in a validation step? What is the difference between a train step and a validation step? No gradient updation. So all we do is we take the batch, we perform forward propagation, and we compute the matrix. That's all we do. And now, what do we do actually in train and validation? We loop over the epochs, PyTorchers, my friend, you will fail. We loop over the epochs. We loop over the data loaders. We loop over the data loaders. We get the batches. We get the new state and the training matrix calculated on the training data using the trainState function, and we have a validation loop which loops over the validation data set, uses the matrix, accumulates the matrix, and logs it on weights indices. That's all. That's all there is to writing a trainState using JAX and FLAGs. Like PyTorch, every time you will have to define the train and validation step, and you will have to put it in a loop. And if you want to perform test on top of it, like this is what I do is just iterate over the test data set and just perform the eval step at the end of the validation step and log it to its classes as a scalar. That is it. And you can see like I just printed out the accuracy and the losses every time. So if I go to the respective its classes dashboard, it looks like this. So as you can see, the losses have gone down, the accuracy has gone up, and the test accuracy and the train accuracy are now just scalars. And if you go to artifacts, you can see at the end of each epoch, we were saving our artifacts, which are saved as artifacts here, and you can access them by just going to the respective artifact and going to the usage tab. You can just, if you want to use this checkpoint for inference or you want to deploy this in future, you can use this piece of code to access this. So that's kind of everything going forward. What's next is you can obviously go to, I wholeheartedly recommend that for learning more about JAX and FLAGs, you first take a primer on JAX, which is very nicely covered by the blogs written by Thing. And after that, basically, you can visit these two particular pieces on Fully Connected, which is the Basic Basis blogs. And every content on Fully Connected is completely free and open source. You can, to see any material related to the talk I covered, you can go and check out my article, which I wrote with my colleague Saurabh Meister, writing a training loop in JAX and FLAGs. And there's also a guide on how to create a very nice unit specification for JAX and FLAGs. And I obviously wholeheartedly recommend to you that check out FLAGs' official documentations, FLAGs' examples, and the awesome JAX GitHub repository, which mentions a lot of sources and repositories that use JAX and flags. And there's one tip which is not written in this PPT, but I'll tell you anyway. If you are ever stuck with JAX and flags, if you are ever stuck in an error, if you are trying to figure out how to do X with JAX and flags, the easiest way or the most convenient and the most intuitive way which we might think is going into the documentation, right? But what we discussed earlier, JAX document sucks AF.
Wait, JAX had documents?
It has doc strings. And flags documentation sucks even more AF. So don't go into the documentation. What you should do is go to the respective repositories, github.com/google/JAX, github.com/google/flags. Go to the issues, uncheck that option, ER is open, remove that filter, and search it there. You will find more treasures, more knowledge in closed issues than you will find in all of the documentation. That's kind of sucks, but it's how the situation is right now.
Is that true for any user code?
No. PyTorch Lightning is pretty new, but it has better documentation. And if you want to access the slide for your future reference, you can either use the QR code or the link given below.
Also the collab notebooks are.
Yeah, and the collab notebooks are linked inside the slide. So that questions.
JAX in Action is also a pretty good upcoming book.
Yes. And I particularly love this repository by Matthias Reich, who is also a Go developer expert in JAX. He has compiled a bunch of basic computer vision tasks into one repository called Flags Models, which shows you how to use a fine-tune a ResNet for an image classification task. Shows you how to train a style GAN using JAX and flags. A lot more interesting stuff.
Or you can just use transformers.
And yes, transformers and diffusers are two of the best things in the whole JAX ecosystem. Like these are amazing libraries which
Natively GPU compatible.
Yes. And that's something I love about Shayaka works on diffusers, as he has mentioned previously. So diffusers is one of the best things in the whole JAX ecosystem. And FYI, if you ever want to use stable diffusion, I wholeheartedly recommend that you use the diffusers pipeline. Am I correct?
Yeah.
Not KRCD?
No,
No.
not KRC because it's not customizable.
So if you don't have any